Good evening, class. We are looking at college algebra practice test number 3, covering chapters 5 and 6. Here's chapter 6, exponential and logarithmic functions is the second part. So reminding you of general properties of logs. Again, log 1 with any base is 0. When the log has the same base as the argument, it's 1. Log base b of b to the power of x is x. And again, take a look at just the arrow in all cases. And again, these two refer to the fact that the logarithmic functions and exponential functions are inverse of each other. Product rule, log xy is log x plus log y, same base b. Log x over y is log x minus log y. All of them have the same base b. Quotient rule, and log x to the power of n is n log x. Both of them have base b. That is called the power rule. So in this case, for number 7, we're going to use the product rule, number 5, and cut it into 3 pieces. Log of x, log of y, log of z, and they all have same base 7. Add them up. For part B, we use the quotient rule, ln of the top minus ln of the bottom, ln 9 minus ln x. For part C, we simply use the power rule, we put the 10 in front. Log of y to the power of 10 is 10 log y. Now, what about part D? We cut it into a few pieces, although it can be done in one shot. So log of the top minus log of the bottom, same base, which is x. Now, log of the top is log of a squared plus log of b to the power of 4, the same base again. And all of these use the power rule. So we put the 2 in front, 4 in front, 7 in front. So the final answer becomes 2 log a base x plus 4 log b base x minus 7 log c base x. Very straightforward, everybody. And in other words, we are comfortable with logarithmic properties. This becomes a piece of cake. All right. What happens here? Understand this means to the power of 1/2 when you have a square root. So log of x cubed y to the power of 5 to the power of 1/2. And using number 7, the power rule, put the 1/2 in front. And then cut it into 2 pieces, log of x cubed plus log of y to the power of 5. We can put the 3 in front, can put the 5 in front. So this becomes 3/2 log x. This becomes 5/2 log y. ln of x over x squared plus y squared, it simply uses the quotient rule. Log of the top minus log of the bottom, in this case, ln x minus ln of the parentheses x squared plus y squared. So we are using logarithmic properties to decompose the log. And of course, we can go the reverse process as well. So this one is as complicated as it gets. Again, it can be done in one shot, but let's do it in a few steps so everybody understands. So first and foremost, we're going to go with number 6, the quotient rule, and say log of the top minus log of the bottom, same base before. So that is number 6 first. So log base 4 of square root of x cube root of 10y minus log base 4 of z to the power of 10. This one is x to the power of 1/2. This is 10y to the power of 1/3. Now this, we're going to use the product rule on that. Log of this piece plus log of that piece. So log base 4 of x to the power of 1/2 plus log base 4 of 10y to the power of 1/3. And this one, we're just going to repeat it. So in each case, now we're going to use number 7, which is the power rule. 1/2 sits in front, 1/3 sits in front, 10 sits in front. In this case, first let's put the 1/3 in front. Now you can cut this into two pieces. In other words, this is log base 4 of 10 plus log base 4 of y. Okay, that means this one, 1/2 sits in front, 1/2 log x base 4. This one, 1/3 log 10 base 4 plus 1/3 log y base 4 minus, with the 10 in front, log z base 4. And we are done. Now, again, with enough practice, you could actually go from here to here in one shot, but various properties are used here, and it's really not a big deal. Now, so we expanded various examples here. Now we want to go back, condense to a single log, if possible. In other words, we moved from left to right. Now we want to move right to left. For example, this one, we are going to go with number 5 going this way. So it's log of 2x to the power 4 times 3x to the power 5. And all you have to do, multiply these two, get 6x to the power of 9. So log of 6x to the power. For part B, we're going to use the quotient rule, and we go from right to left. ln of 6x over to the power of 9 over x squared. And of course, this simplifies to 6x to the power of 7. So ln of 6x to the power of 7. All right, so let me erase my work again. Now for part C, again, I'm going to go with number 5 because I see a plus. Okay, and I want to go this way. So to do that, the very first thing I do is number 7. So that means I'm going to cross the 2 and make it the exponent. I'm going to cross the 3 and make it an exponent. Let me actually erase so it makes it easier to see. So crossing the coefficients. So it's log of x squared times x plus 1. Quantity cube with that. Now, as far as I'm concerned, it's done. But you may have to multiply them through to receive full credit for log, just in case. All right. To do part D, you don't have to move things around, but let's do it to make it easier. First of all, this one goes away and makes this one square root of y. This one becomes 3, and I'm going to put this next to that because both of them have a plus sign. And the idea is you can do it again in one shot, but I want to make sure you understand that these two mean log of x z cubed minus log. Okay, it is there. I don't have to. Okay, let me just. So minus log of square root of. Okay. And now I'm going to use number 6, the quotient rule, because this is positive, this is negative, and I'm going to go this way, log of this piece over this piece, x z cubed over square root of 1. That's how you bring it into a single log. We want to solve exponential equations. Please understand that if these two are equal with the same base, they must have the same exponent. If they are equal with the same exponent, they must have the same base. So because these two have the same base, they must have the same exponent. Divide both sides by -3. X becomes -1. As always, you can try it by putting it back always into the original equation only. What about this? Okay. We either have to come up with the same base or the same exponent. I hope you recognize that if this is the base 4, this one we can change it to base 4. This one we can change it to base 4 as well. 64 is 4 cubed, 16 is 4 squared. So the right side remains unchanged. The left side is 4 to the power of the sum of those two, according to the exponential rules. So now they have the same base 4. Then they must have the same exponent as well. And if they do, subtract, and you get -1. Divide, and you get x equals -1/3. We're going to continue with more equations. In this case, we want to solve for x. Number 1, divide by 2. Number 2, in order to get to the exponent, you have to take a natural log, everybody. If I take a natural log of the left side, according to the fact that exponential functions and logarithmic functions are inverse functions, they undo each other, they give us 3x. So basically, divide both sides by 3. Now, this is the exact answer. Always write your exact answer. If you put it into a calculator with a bunch of decimals, you get 0.62393. Bear in mind, if they don't ask you for how many decimals, that means they want exact. Okay. Now, you may recognize this as, in essence, a quadratic in form, or you may not. If you recognize it, you want two numbers. The product is -6. The sum is -1. And this is e to the power of x, quantity squared. So you can write e to the power of x, e to the power of x. And now the two numbers would be -3, +2. This is what we get. Okay. Now, this is the way to do it. However, if this is hard to follow, you can go with the following. Let e to the power of x be anything except x, for example, y, then this becomes y squared minus y minus 6 equal to 0. And this can be factored into y minus 3y plus 2 equals 0. And you replace the y and you get here. In other words, do you have to do it by substitution or not? That's your choice. Okay? In any event, in this case, e to the power of x is 3, in this case, negative 2. And I hope you remember exponentials. The y coordinate is from 0 to infinity, so can't be 0, can't be negative. This is out. So if e to the power of x is 3, x is ln 3. Again, let me just erase the work first. You take the ln, this becomes x. So x equals ln 3. It's an exact answer. Roughly 1.0986, depends on how many decimals they ask you. Always answer exact, unless otherwise asked for. And normally they will ask you how many decimals. So we are looking at exponential and logarithmic equations. Log base 3 of 9k equals 2. We want to solve that just as we did with the exponentials. If two logs are equal, they have the same base, they must have the same argument. If two logs are equal, they have the same argument, x and x, then they must have the same base, a and b. Needless to say, all the arguments, all the bases must be positive, okay? All right. By the way, the base can't be 1 either. So all you have to do for this one, look at the arrow. 3 squared is 9k, or 9k is 3 squared. 3 squared is 9. So divide by 9, k becomes 1, and you're done. It's that simple. Log 4 plus log of negative 5x equals 2. In order for you to solve a logarithmic equation, everybody, you must bring it to a single log. So this one follows number 5, the product rule, and we move this way, becomes log of 4 times minus 5x, which is log of negative 20x equals 2. Now, remember, when we have LOG and no base, we have a common log. The base is 10. And again, look at this arrow. The base is missing for LOG. That means the base is 10. Okay? We can look at this one. So, negative 20x is 10 squared, or 10 squared is negative 20x. Makes no difference. Of course, 10 squared means 100. Divide by negative 20. X is negative 5. And you have to always check. This one doesn't have x, no worries. This one, negative 5 times negative 5 is positive 25, it's okay. The argument must be positive, okay? And it is positive when you plug it. Log base 7 of 5n minus 2 equals log base 7 of 8 minus 5n. We see both sides having only one single log, okay? And they both have the same base, so they must have the same argument. We move things around. 10n equals 10 and n equals 1. And you're done, but you can quickly check to make sure each argument is positive. If I put 1 here, I get 5 minus 2, 3. And if I put 1 here, I get 3. Obviously, they're the same. But more importantly, each argument must be positive. Now, again, the way you uh, work with logarithmic equations, if they are all logs and nothing else, each side you bring it into a single log. If you have logs and numbers, you bring all the logs to one side, all the numbers to the other side, then you bring the logs into a single log and you go by definition. In this case, both sides have logs. So the left side, there's nothing you can do, but the right side, you can do number 5, the product rule, and make it log of x times 12 or simply 12x. The left side doesn't change. Now they are both the same base, namely the base is missing is 10. They must have the same argument, meaning x plus 12 and 12x must be identical. We want to solve for x. We move this minus x. So 11x, x becomes 12 over 11. Again, an exact answer. Please don't change it to decimal unless they, for some reason, ask you. All right, we are looking at more equations. Again, we notice both sides have logs and nothing else. So we bring each side to a single log. The right side has a single log, but the left side, we can use the quotient rule to bring it into a single log. So it becomes ln of x plus 4 over x. On the right side, we don't have to do anything. Now they have the same base, namely e. They must have the same argument, x plus 4 over x, and x plus 1 must be identical. To solve this, we do cross product. Multiply these two, you get x squared plus x. You multiply these two, you get x plus 4. Now you don't have to move anything because x and x cancel out. X squared becomes 4. Therefore, x is plus minus square root of 4 or plus minus 2. So let's check. If I put the 2 here, 2 plus 4 is positive, 2 is positive. I put minus 2 is fine here, but not good here. I don't even have to check here. If one of them fails, never mind. Negative 2 is out. Again, it works with this one, but you have to continue checking with each and every one of them. It fails with this one, I'm not going to move on anymore. It's out. So we had logs on both sides. Now we have logs on one side. Now, even if we had on both sides, but we had a number as well, we would move things around such that all the logs are together. Now, these two can follow number 5, the product rule, and come together as a single log. So this becomes log base 2 of x times x minus 1. The right side doesn't change. And now, because it's a single log, you go with the definition and you say the argument is 2 to the power of 1. So x times x minus 1 is 2 to the power of 1. This is x squared minus x equals 2. Move them to the left. You want two numbers. The product is -2. The sum is -1, -2, and +1. So x is either 2 or -1. We're going to check. When I put the 2 here is fine. 2 minus 1 is +1. That's fine. We are done with that. When I put -1 here, doesn't work. Done. It's out. So you must check. Again, every argument must be positive. Even 0 not acceptable. Four to the power of x plus 10 equals 3. Subtract, you get -7. 4 to the power of x, 2 to the power of x, 10 to the power of x, e to the power of x. Any exponential equals a negative number, there is no solution. It can't even be 0. Remember, that really refers to the y coordinate. That means the range is from 0 to infinity, so there is no solution. 4 to the power of x can never be negative. Now, 7 to the power of x minus 10 equals 1. 1 can be any number to the power of 0. So since the base is 7, make it 7 to the power of 0. And so now you have same base 7 on both sides. If they are equal, they must have the same exponent. X minus 10 must be 0. X becomes 10. And I hope if you check it, you see that it works. Now, 4 to the power of x equals 9 to the power of x minus 2. This is as difficult as it gets, because one easy way is to find the same base or the same exponent. We can't. So how do we move on? Well, we really don't have a choice. We are solving for x, the exponent. You can take a natural log or a common log. But I want to make a point of, if any of them was e, you would definitely get a natural log. If any of them was 10, you would take a common log. But since it's neither, then it doesn't matter. You can go with natural log or log, and I'll show you what happens if you choose differently. So reminding you, when y equals ln x e to the power of y equals x, and ln of x to the power of n is n ln x. So if I take the natural log of both sides, then x becomes the coefficient. That's what we are talking about with this one. So this is one of the properties. X times ln 4, x minus 2 times ln 9. What's important for everybody to know, ln 4 is a number. It's not missing. So is ln 9. But we keep it as ln 4, we keep it as ln 9 because we want them exact. Okay? So this is x times ln 9. This is minus 2 times ln 9, the right side. Since we are solving for x, we have a choice of moving x to the right, this one to the left, or just move this one to the left. The reason I'm going to move this one to the right, because if I move this one to the left, I create too many negatives. I'll tell you the difference also in a moment. So I'm going to subtract this from here, and I'm going to move this. In other words, this I move it this way, this I move it this way, this is what I get. Now on the right side, I can take the x out. Very straightforward. So what happens? X times ln9 minus ln4. Again, please bear in mind, ln9, ln4, those are numbers. So all you have to do, divide by the parentheses ln9 minus ln4. Now, this is an exact answer. First, let me show you the approximation. If you use a calculator, you get this approximation. That's not what we want unless they ask. Okay. So I want to make sure everybody understand that. Okay. Now, I want to go back here. If we moved it the other way, then x would have become, take a look, minus 2 ln9 over minus ln9 plus ln4, which I hope you see that this is identical to this one. All you have to multiply by negative on the top and the bottom. That's one thing I want to make a point of. The second point, if instead of ln we took the log here, then this one would be x equals 2 log 9 over log 9 minus log 4. Okay? We are not saying 2 ln9 is the same as 2 log 9. No, we are saying this ratio and this ratio are identical. So in this case, whether you take a natural log or a common log makes no difference. But as I mentioned, if any of the base was e, must use natural log. If any of the base is 10, must use common log. Okay. Now, we want to find log 50 base b when log 2, log 3, and log 5 base b is given. When that happens, class, you have to cut this into pieces so it contains only those factors, 2, 3, and 5. And I hope you know that 50 is 2 times 25 or 2 times 5 squared. I mean, you can factor it. You should know. We've discussed the factor about the prime numbers, 2, 3, 5, 7, 11, 13, 17, and so forth. So you divide by 2, you get 25. Is it divisible by the next one, which is 3? No, 5 gives you 5, 5 gives you 1, and this is what you get. And now you use this. You get log 2 plus log 5 squared, same base b. And then this one, the 2 sits in front. In other words, we are using the power rule on that. And now you can replace the first one with a 2 times c, and you're done. Okay. So that's very straightforward, everybody. What about this one? We want log base b of the 5th root of 300. Again, we are continuing. This is part B of the question with the same given log 2, log 3, and log 5. All of them with base b are given as ABC. Let's see how we do the math. Number one, this is 300 to the power of 1/5. Number two, we can use the power rule. Look at the power rule. We bring number 1/5 in front. Power rule, number 7. Now we're going to cut 300 into pieces. So I'm going to, again, work on that. Something that you should have no problem with, but anyways. So we have 300. If I divide by 2, I get 150. 2, I get 75. Can I divide by 2 anymore? No. 3, 25. Can I divide by 3 anymore? No. 5, 5, 5, 1. This is where you stop. And this means 2 squared times 3 times 5 squared. So you're completely decomposing the log now. You have a chance of doing so. So 300 is 2 squared times 3 times 5 squared. Now this is log of 2 squared plus log of 3 plus log of 5 squared, and then 2 sits in front, 2 sits in front, 3 doesn't have any. I hope by now, with all the examples we've done, you can go from here to here using number 5, the product rule, in no time in conjunction with the power rule. So 1/5 remains. This becomes 2 log 2. This becomes log 3. This becomes 2 log 5. All of them have the same base b. And now we're going to replace log 2, log 3, and log 5 with ABC. So the answer is 1/5 2a plus b plus 2c. 1/5 times 2a plus b plus 2c. So very straightforward derivative. You're going to move on, everyone. In short, we used various logarithmic properties to come up with the answer. A nuclear reactor contains 200 grams of radioactive plutonium-239, and plutonium decays according to the formula A equals A sub 0 e to the power of negative 0.0000284 T. How much will remain after 5,000 years? And the concept of exponential growth versus exponential decay. Exponential growth, we have the concept of doubling time. Exponential decay, we have the concept of half-life. And normally something like this, n of t equals n sub 0 e to the power minus kt. So first of all, in this case, what is given when we read this question? It contains 200 grams of radioactive to begin with, that is A sub 0. So A sub 0 is 200 and T is 5,000, everybody. That's the given. So for this question, basically replace the A sub 0 with 200, T with 5,000, and all you have to do is just put it into a calculator. So you put this into a calculator, you multiply these two, you get negative 0.142, you raise e to the power times 200. And in cases like this, they normally tell you how many decimals, because it's an approximation, everybody, to begin with. Okay, it is an approximation to begin with. 173.552 grams, meaning 200 grams of plutonium decays to this much after 5,000 years. Find the half-life. As I mentioned, the concept of a half-life, how long does it take for a substance to go to half of its size? In this case, 200 goes to 100, but you really don't need to know how much you begin with. Okay, so half-life is the time required for a quantity to reduce to half of its initial value. So if we stick with that, we don't even worry about that. We don't even know what that is. Half-life means A has changed to half of initial value. A sub 0 is the initial value, or in this case, n sub 0, it doesn't matter. So half of A sub 0 is A sub 0 e to the power. And why is it that it doesn't matter? Because that crosses out. Let me just, they cancel out. So even if you put the 200 class, so you put the 200 here, you have to put 100, so you get the same 1/2. Now, Because you want to get to t, which is the exponent, you're going to take a log. Which log? Because the base is e, clearly we're going to take the natural log. This right side just becomes the exponent when you take the log. So we have ln of 1/2. You can write it ln1 minus ln2 or not. And of course, ln1 is 0. Okay. And so t becomes this number divided by this number. And now you put it into a calculator, and it says it takes 24,406 years, roughly 0.59, to get to half of its value. And that's the idea. Okay. Now, one thing I want to add, the continuous rate of growth is R or K or the number sitting next to T without the negative or positive. The continuous rate of decay is negative R or negative K 0.000284. Okay. Depending upon whether you use the exponential growth or exponential decay. Okay. Either way, this number, if it was an exponential growth and this is not, you wouldn't have a negative here. That would be considered the continuous rate of growth for a positive case, for a negative decay. Because the moment you mention decay, it means negative. Now, I want to show you how to find actually the half-life in general, never mind this one. So if you look at this one, half-life, that means n sub 0 is the original value. Half of it is left. Again, like I said, they cancel each other. And now we're going to take the natural log of both sides because you want to get to t and the base is e. That's why you take a natural log. And the left side becomes ln1 minus ln2, which is minus ln2. ln1 is 0. And so if you want to either solve for k or t. If you solve for t is ln2 divided by k. If you want to solve for k, k equals ln2 divided by 2. So it's very straightforward.